Hello and welcome to the Engineering Circuit Analysis Tutor. I'm very excited to teach this course because I'm an electrical engineer myself, so I was always very interested in electricity and electric circuits and things like that. So what we're going to do in this class is exactly what the title is. We're going to learn all about circuits, we're going to learn about electricity, we're going to learn about the components that go into circuits, but mostly what you do in engineering courses is learn how to analyze them. Given a circuit, what is going on? Where is the current going? What is the purpose of the circuit? And so there's a lot of details there and a lot of techniques that have been developed over the years to pull those things off. You know, 100 years ago, circuits and all of the things that we take for granted today would be super theoretical. But they're all basically physics. They're taking energy out of a battery or energy out of a wall and letting it run around in a loop and doing some useful work with it. That work might be spinning a motor, right, to spin a fan. Or that work might be shooting a radio wave out across the world to talk to somebody else. Or that work might be to go into a microprocessor and, you know, flip a bunch of bits around and add a bunch of numbers together, basically create what we call a computer. But there's basically infinite number of ways that you can create circuits to do what we want them to do. But before you can understand a microchip, before you can understand an amplifier, before you can understand a nuclear power plant, you have to start at the basics. You have to start at the really, really simple questions, the things that are so fundamental. And that's what we're going to do in this course. We're going to start with fundamentals, and then we're going to go on and talk about circuits and the different kinds of circuits, how to analyze circuits, figure out what's happening inside these circuits. And you'll find that there's a broad array of tools that you'll learn in your classes to help you with that. Now, I'll say right away, the title of this guy is Engineering Circuit Analysis, but my goal is to really try to make it as accessible as possible to anybody out here who wants to learn it, right? Don't let the word engineering scare you too much. Engineering is a big word, makes it sound really hard, but I'm going to try to break things down so that everyone can get it. Now, I will say the good news is, and this is true, with circuits in general, there really aren't that many big picture concepts to understand. In this section, we're going to talk about voltage, current, and resistance because they're so important. But really, once you get past that, there's a few other big picture concepts, and then you understand really the basics. The challenge with circuits comes is that I can draw a circuit on the board, and you might know how to analyze it and figure out what's going on. And then I might change one little line, one little branch of the circuit might completely change how the thing operates, right? So there's an infinite variety in how they can be constructed. That's what really requires you to get a lot of practice. And that's what this course is going to be. It's centered around practice, 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 practice. And to be honest with you, you don't need to know much more than algebra to do very, very well in this class. Yes, we are going to use complex numbers a little bit later on, later in the course, not in the beginning. We are going to use some calculus, some integration later on in the course. But by and large, you can do a ton of circuit analysis with just some basic algebra. And that's the way I'm going to try to teach it to you so that, you know, it can be accessible to everybody while also catering to the engineering student, which is really the focus of the class. All right, so I had to figure out where to start. I think the most important thing for everyone watching this to understand is the concepts of voltage, current, and resistance. Because those three things we're going to end up zooming in on and talking about for the next many, many hours. And you really have to understand what they are. A lot of students, if they haven't already had an interest in circuits, they get very confused at what the difference between voltage and current is and how does resistance play into that. So what we're going to do in this particular section is zoom in on that, and I want you to really make sure you internalize and understand what they mean, because as you go and solve a circuit and I'm asking you what the voltage is, you need to kind of have an internal picture of what that means even before you do any math. So there's no math in this section. You know, this is all definitions. I try to make it as interesting as I can, but it's so incredibly important. Make sure you understand this. First things first, I think we all know this. What is an electric circuit? What is a circuit? I mean, a lot of people think they know what a circuit is, and most people probably do, but what is a circuit? The simplest one-sentence definition is it's a closed loop that carries. What does it carry? What do you think? Electricity. You know, like I say, I have to start somewhere. And I never assume that you know anything about what I'm talking about. So a circuit. You think about a circuit of a racetrack or a circuit in the Indy 500. It has to go all the way around. If you don't have it going all the way back around to the starting point, then you don't have a circuit. And no electricity can flow in such a situation unless it goes all the way back around to where you start from. So, in order to have a circuit, it has to come back to where it starts from. So a simple example of that, without really getting into any kind of detail, is, here's a source. I'm going to put a plus minus to denote it as a source. This could be a battery. This could be a battery that you pull out of, you go buy it at the store. And we're not going to put anything in the circuit with it. We're just going to draw these lines here. These lines are wires. So it would be just like you might think. You get a battery, you hook a wire up that goes all the way back around to the other side. This completes a circuit. The electricity can circle around and around and around here, coming from one terminal back around to the other one. That means it's a circuit. Super, super important, but also very simple as well. Now let's get to something that's not quite so simple, but a lot of people still may understand this. What is current? And when I say current, I mean electric. You've got to learn how to spell current, first of all. Current. Electric current. What is electric current? Okay, the simplest definition to write down for what electric current is, it is the flow of electrons in a circuit. It's the flow of electrons in a circuit. So everybody's heard of current, electric current. An analogy to electric current would be current in a stream. We all know what a current is in a stream, right? It's when the stream is moving. There's a current. It's pushing your boat, right? It's the movement of something. Don't confuse that, because a lot of people get confused with voltage and current if you're not really familiar with these terms. Voltage has really nothing to do with anything moving. We'll talk about what voltage is in a minute. The current, the electric current, think of a stream, think of something moving. That is what's moving. So in real life, if you have a piece of wire, which is metal, the electrons are really and truly what's moving around in that wire. So if you wanted to kind of zoom in and draw a little picture of that, we could draw another little circuit here, a little simple one anyway, like this. Goes up, connected all the way back around to the beginning. So there's going to be current circulating around and around and around. But if I zoomed in, let's say this is a piece of wire, right? If I zoom in this wire and get a microscope up on top of it and zoom in on it really, really tight, if I could see that, what I would see inside is a bunch of atoms, right? So this atom is going to have a positive nucleus, and this atom is going to have a negative electron orbiting around this atom. Now, in real life, this might be, copper wire. So there'll be lots of protons in the nucleus and lots of electrons. But for the purpose of this drawing, just pretend that there's a positive center and there's a negative things orbiting. Now here's another atom here. It's got a positive center and it's got a negative thing orbiting. This one's got a positive and a negative. Every atom has this positive center and negative surroundings. Now in metals like copper and gold and silver that conduct electricity well, these electrons, they're not really tightly held to the atom. They're there, but they can be coerced, so to speak, to move. They can be, you can talk them into moving if you try hard enough. The object that actually talks them into moving is the battery, right? Is the battery, or the source coming from your wall, for instance. And when that happens, when you hook a battery up to this wire like this, since these electrons are not really, really held on terribly tightly, what happens is this electron, down here, this electron is going to jump, literally, it's going to jump over and grab it and go into the orbit of the next atom. And at that moment, the same time that happens, it's a chain reaction. This guy goes to the next guy. This electron moves to this guy, and this electron moves to its adjacent atom. And this process happens almost at the speed of light, so you can't see this electron movement, but that's what's in fact happening. So it's a chain reaction, and they're almost like in lockstep, moving from one atom to the next. And this movement is really, you can think of it as energy of motion, is the energy that the circuit uses to do whatever it's going to do. Turn a fan, turn a light bulb on, whatever. That's where the energy from the battery is going. It's going into pushing these electrons around, which is electric current. So when I draw this here, I'm drawing these negative electrons moving. So this is what we call electron current, or electric current. There's another way to say that. So the electrons, if you want to think of it this way, we'll go draw it down here. This is the negative terminal of the battery. This is where the negative charges are sort of piled up. So here This is called the electric current. So the electrons literally bleed out of this negative terminal, they go all the way around, and they go back and they enter it back into the positive terminal because this is positive, so it's going to attract the negative electrons. And this process goes on and on and on until the battery basically dies out if it's a battery and it can't supply any more electrons, or if it's a wall, it just keeps going and going forever and you get charged for it, right? It comes from the power plant. But the electrons are really and truly what's moving. Now, let me blow your mind a little bit here. In a basic circuits course, like a hobby book, like, go to Barnes & Noble or somewhere and just get a book on electricity. They'll talk about the electrons moving. But when you get into engineering and you really start trying to analyze how a circuit's going to really behave, it's a little bit cumbersome to talk about the electrons moving, even though that's really what's happening in real life. The reason that it's a little bit cumbersome is because of really one reason. Electrons have a negative charge. They have a negative charge. And what we're going to do later on is we're going to have a circuit and we're going to write equations, simple algebra equations, so don't get too worried about them, but they're going to be equations, and they're going to describe how the current is moving. If we do that for a bunch of negative electrons, then we're going to have negative signs running around all of our equations for our electric circuits. And that would totally work, totally work. However, it's a little cumbersome to have negative signs running around all of our equations. So in real life, from this moment on, I'm just teaching you this to give you background, but from this moment on, we're not really going to talk about electron current flow or electric current flow. We're not really going to be talking about the direction that the electrons are moving. Let me show you what we are going to talk about. In this very same wire, you may have to stare at this a little while to realize this, but I think you should be able to convince yourself that since this charge is jumping this direction, for a temporary moment, like we're talking about a chain reaction, right? This one moves here, then this one moves here, and this one moves here. But at the very moment that this negative charge jumps away, for a split second, this atom has lost an electron, right? So it's an electrically neutral atom. It's zero charge altogether because the electrons and the protons cancel out. They're the same number. But as soon as I lose one of these electrons, I have sort of a positive charge left over. Right? Same thing happens here. When I lose this guy for a split moment, I have a positive charge here. So as these negative charges jump this direction, mathematically it's the same thing as pretending that I have positive charges jumping this direction, the opposite direction, because this guy's lost an electron and then the guy before it loses one and before it. So as these guys move this way, it's the same as saying mathematically a positive charge goes the other direction. I hope that makes sense to you qualitatively based on my drawing here. But if it doesn't, all you really have to remember is that the real current that we talk about in engineering is called the whole current. And it goes in an opposite direction from the electric current, which is the real life thing that's happening. And it's a mathematical convenience. Because since now, instead of talking about negative electrons moving this way, we talk about positive charges moving this way, now we have positive charges in all of our equations. And all of our equations have rid themselves of all these negative signs, or at least a lot of the negative signs, right? And it makes it a lot easier to deal with. So it's really saving you time, if you think about it that way, saving you a thought process. So the real electrons are going this way, but we pretend that we have an equal and opposite number of positive charges going the same direction. We call it a whole current. The reason it's called a whole current is because for a split second, when this electron leaves, it's left like a hole behind on this atom, which is making that guy positive. So the whole current actually comes out of the positive terminal like this, right? And we denote that current I in electrical engineering or in engineering, and it's the whole current. This is such an important concept that you really should not go on until you truly internalize and make sure. Basically, all you need to remember in the big picture is that anytime you have a circuit, the source is going to always have a positive and a negative terminal, always, just like any battery. If you pull a battery out of the box, you'll see one side's labeled positive, one side's labeled negative. In real life, if you hook the battery up to something, electrons are really the objects that come around from the negative terminal back to the positive. But in electrical or in any kind of an engineering course when you're taking a circuits class, you never, ever, ever talk about the electron flow in this direction this way. You always instead talk about the positive current flow. It's the same value going in opposite directions. And it makes the equations much, much simpler. And in fact, all the power calculations, the function of the circuit, the energy, everything is completely and totally described by talking about this sort of like this pretend current that's going in the opposite way. So just get used to seeing that. You're always going to pretend that your current's coming out of the positive terminal, even though in reality the electrons are bleeding out the other side. Now, the units of electric current. I told you briefly, current is denoted I, right? I. It probably is some history to it. You could go look it up. You would think current would be called C, but it's not. It's called I. So anytime you see I labeled in a circuit, that is the electric, or that's the current flowing through that branch of the circuit, or something of that nature. Now, what are the units of current? A lot of you have already heard this. Units, let's go ahead and change colors a little bit. The units for current is the ampere, which is also called an amp, right? Or you can call it simply A, right? The higher the number of amps, the higher the current going through the circuit. Basically, an ampere is telling you how many charges are moving through your circuit per second. And there's a definition in physics that you could go look up for that, and that's fine. It's not terribly important because, really we're always talking in circuits. In a physics class, you'd be talking about an individual charge moving. There's so many coulombs on a charge moving, right? But in a circuit, you've got billions of charges in this guy. So you don't talk about coulombs and how many coulombs of charge are crossing through a boundary. You just look at the aggregate, which is how many amperes, which is a coulomb per second. How many coulombs per second really are going through that guy? So an ampere represents how many coulombs of charge are passing. If you were to slice this wire and watch how many go through there, that would be how many coulombs of charge go through there per second. But really, you don't have to deal with that too much in a circuits class. We're always going to be talking about amps or amperes. So bringing it back to the everyday language that everybody already knows. You've heard of amps, right? Everybody's heard of amps. That is the current flow. The higher the number of amps in that circuit is the more it can potentially kill you, right? It doesn't take much current to kill a person, actually, believe it or not. So you might have a car stereo that has, a 10 amp amplifier, right? It means 10 amps of current are flowing around that amplifier because to push the sound into those speakers and get them to move really loud, you need a lot of physical electricity to do that, right? To actually get it to move like that. But in a computer, inside of a microchip, you might have a teeny tiny amount of current going around because those are very delicate circuits. You might have a milliamp or a microamp inside of those guys. But the base unit of current is always going to be the ampere, which is what we have right here. All right. So to sum it up, which is really so important, I keep talking about it, current in general in real life is the flow of electrons. However, in all circuits from henceforth that we're going to talk about, we're not even going to talk about this. We're just going to say the current comes out of the positive terminal and the unit is ampere. That's really the bottom line. All right, now the next thing we have is the concept of voltage, which many people get confused with current because it's kind of used interchangeably. Voltage is the push, I'm going to put in quotes, the push that causes the current to flow. So in other words, it's the source, right? It's the source. So when you look at a 9-volt battery, that battery comes in a physical size. It has 9 volts. 9 volts is a relative indicator to tell you how much oomph, for lack of a better word, that battery can push in a circuit. So the current and the voltage are very, very closely related. You cannot have any current flowing without something pushing it. And so you have to have some source there to push it, which is usually a battery or a wall socket or something like that, and that's always measured in volts. So when you see on TV, oh boy, you could be killed by 10,000 volts. Well, 10,000 volts is not really how much current is flowing through you. That's just how much push there is. So to kind of bring it down to layman's terms, think about a straw. Pretend this were a soda straw that you get at a restaurant, right? And let's say it's a pretty narrow straw, almost like a straw that you use to stir your coffee, okay? Now, if I blow on it like this, then I'm going to be pushing air through that straw. The current is the air that's actually moving through the straw, right? That's what the current is. That's what's actually doing the movement and doing the work, all right? Now, I'm actually blowing on it, so I'm pushing, I'm actually increasing the pressure at the end of that thing. That's causing the current to move. That's the voltage. The push that I give it, the pressure that I give it, is what's actually causing the current to move, or in this case, the air to move through the straw. If I don't blow and I don't give any pressure, then there's no current, there's no flow of air through the straw. Same thing in a circuit. If the voltage is 0, coming out of the source here, then there's no current. So the two are very closely related. It's just that the voltage is the push and the current is actually what's moving. That's really the main thing to take away from this guy. So it usually comes from, where it always comes from, a battery or some kind of other source that you might get that's generated out of the wall. Now, for the units of voltage, the units is the volt, or simply call it V. So that's just that's the same thing as the current. The more volts you have, the higher the voltage you have, the more potential to move current through a circuit you have. So that's why 10,000 volts is so much more dangerous than 1 volt. It's not because it's measuring how much current's going through your body. It's just that if I grab onto a 10,000 volt fence, it has the potential to push a ton of current through my body, right? Whereas a 1 volt source, since it's so much less of a push, so to speak, it's not really going to do very much to me. Right, so that's really the main difference. So current and voltage tied at the hip, but two different things. The biggest faux pas you can kind of get into is saying, boy, that was a really impressive circuit. That had 39,000 volts of electricity flowing through your body. That sentence makes no sense. Voltage does not flow through your body. Only current does. Voltage is what actually pushes the current through your body. That's really the main distinction. Now, tied to all of this is the very, very important concept of resistance. All right, resistance. Resistance is very, very simple to understand. It opposes the current flow in a circuit. This might be a little bit confusing at first, but think about our soda straw, all right, for a second. Pretend for a second we didn't have actually a soda straw. Let's say we had something really big, like a paper towel tube. Like, you get the paper towels at the grocery store, and there's a giant cardboard tube in the middle. And I stick that to my mouth and I blow. It's pretty easy to blow through a paper towel tube because it's so big, right? So I can blow all day as long as my lungs can do it. I can blow lots and lots and lots of air through there, right? With really not much effort. I don't really have to push that hard to actually make that air move because it's just so big. So we say that the resistance, for lack of a better word, of this guy to airflow is not very big. It's got a low resistance, right? Now let's compare and contrast that. Let's go back to our coffee stirring straw. Very, very tiny diameter. So for that one, to get any kind of air movement through it, I've got to blow pretty hard. And I can feel it in my lips. I'm really blowing because we say that the resistance of that smaller straw is much higher. The resistance to airflow is higher because it's physically constrained. You cannot force that much air through that straw very easily. I mean, you can do it, but you have to blow really hard. So we say the resistance is much higher for that guy. And actually, that analogy directly translates to electric circuits as well. If I literally have a wire, a copper wire as big around as I'm demonstrating here, this big around, it has a very, very, very low resistance. The cross-section is so big that tons of electrons can move through there, tons of electricity can move through there without really much resistance because it's so big. But if I go get a wire thinner than my hair, or maybe I go get a tiny wire etched onto a computer circuit chip, which are so small that you have to have a microscope to see them, then the cross-section of a teeny tiny wire like that is going to be so small, it's going to actually resist the current. The electricity is going to get to move through there, but it's going to cause friction. There's just not as many atoms there for it to move. So the resistance is going to be higher. So if the smaller the object, the resistance is always going to be higher. The bigger the object, the resistance is going to be smaller. So think of it that way. It's resisting and it's opposing current flow, not because something intelligent is in charge of it, it's just because of the size of it usually, or the way it's constructed. So current, voltage, resistance, they're all so intertwined because of the analogy with the soda straw really. The resistance, when the resistance is smaller, like the big paper towel tube, right? Then I can move a lot of air, a lot of current, without much effort, with a lower voltage, right? And when I go to a smaller straw, I can still move current, but it's going to take more effort, more voltage, to get the same amount of current to flow, or to get the same amount of current to flow through that resistance. So current, voltage, resistance are really all tied at the hip, really, as far as being interrelated. Now, the units of resistance, the units, is called the ohm. Ohm. But you never actually write ohm in a circuit. You always use this omega, this capital omega. And so when you have a 5 ohm resistor, has more resistance than a 1 ohm resistor. A resistor we'll talk about in the next section, but they actually have a circuit component called a resistor whose job is to resist current flow. Seems weird why you would ever need that. We'll get to the reasons why you would need that later, but that little guy is going to try to stop the current to flow to up to a certain point. And so the higher the value, the more it's trying to resist the current flow, right? Just like the little examples that we were given before. So, very, very important topics. Current is the flow of electricity. Voltage is how much push you are pushing to make this current flow. And you're always flowing through something. That something is always going to have a resistance. Different size wire, different resistors, different circuit components are going to manifest themselves as different values of however many ohms. Now, for all of these guys, I've kind of hinted here, but I'll just spell it out. We can use the metric prefixes for all of these guys, right? Because these are standard units. We can use the metric prefixes. So for instance, if you're talking about amps, which is current flow, it may not make sense to talk about amps. You might need to talk about milliamps, right? Milliamps, just like a millimeter. That's 1/1000th of an amp, right? Or you might talk about microamps, right? 10 to the minus 6 amps, etc. Something like this. Right? So the base unit is always amps. It's just you have a metric modifier on the front. You might have resistance, how many ohms you're talking about in the circuit, but it might make more sense to talk about milliohms if it's a very small resistance, or even if it's tiny, tiny micro ohms, right? That's 10 to the minus 6 ohms, right? Or if it's a large value, maybe you have kilo ohms, or maybe you even have mega ohms, which is millions of ohms. Right? Or here, kilo ohms is thousands of ohms. So the metric system applies here. There's nothing special. And for voltage, maybe you have millivolts, maybe you have kilovolts, maybe you have megavolts. Maybe a nuclear power plant is operating at so many megavolts or something like that. Very, very important concepts. I can't stress them enough. So we've talked about current, we've talked about voltage, we've talked about resistance in detail. Because it's so important for you to understand what that stuff is. It'll make my job easier whenever we start talking about circuits that you're not scratching your head. What's the voltage again? I can't remember. I mean, I really need you to understand that before we get to anything else. Now, let's talk about some general things that you probably heard growing up. General definitions, so to speak, that you probably heard. First one is DC and AC. DC versus AC. Let's talk about that for just a second because it's something that we need to make sure you understand. DC. This stands for direct current, right? And basically what it means is constant current flow. Basically, all of the batteries you've ever used in your life, the AAAs, the AA's, the 9 volts, watch batteries, I mean anything. Anything built into a little device that we call a battery always generates a direct current. It means that when you hook it up to the circuit, it's giving you a constant voltage at the source location, right? That's pushing current around. And because it's a constant voltage it's providing, the current that comes out is constant, never changes. Now, in reality, the battery is going to die down and it's going to get weaker and weaker, so the current does eventually bleed off. But I mean, if you take a snapshot and look at it, the current is a constant. It's called direct current. All right, now let me contrast that to AC, which I know you've heard of, and that's called alternating current. Alternating current. And this means, well, exactly what it sounds like. It's a wall socket, and it means the current, for lack of a better word, moves back and forth. And this is really actually much easier to understand what the purpose of a drawing here. So let's draw a quick little circuit like this. Now normally we've been putting plus minus, but here I'm just going to kind of put a little wave in here to kind of indicate to you that this is alternating current. And we'll get into all these symbols later, you know, in detail. I'm just trying to get the idea out to you. What this means, and this is a great model for what's happening in your wall socket when you plug something in, you know, into the wall. What happens is at first the current comes out this direction and flows this way, and then it starts to slow down, and then it goes back the other way, like this. And then it goes back the other way, and it goes back the other way. It literally alternates the direction of the current. If you could actually see the electricity coming out of your wall, like I'm looking at a plug right now over there in the wall. If you can visualize a plug, you know, everybody kind of thinks and realizes there's electricity coming out, but if you could see the electricity, you would see the electricity racing out and then slowing down and then going right back into the wall and coming out the other way, and then racing back into the wall and coming back the other way. And it alternates back and forth, back and forth, back and forth, back and forth. How many times does it do that? Well, in the United States, it's 60 times a second, 60 hertz. That's a unit of frequency. That's how fast it's coming back and forth. 60 times every second, that electricity is switching directions, right? Now, you might say, I should say, the number one question you get when you explain alternating current and direct current is, why do we have a difference? Why do we have a difference? Well, the reason mainly is a lot of history, actually. But truthfully, whenever you generate electricity at a power plant to feed houses, it's much easier to generate it as an alternating current. And it's much easier to transmit it out to the homes as alternating current. And that goes into a lot of theory that I can't get into right now, but just trust me on that. It's a little bit easier. You know, really, all of our power plants, whether they're gas or nuclear or coal or anything, all they do is generate a lot of heat, and that heat heats up steam usually, and that steam turns a generator. So all of our power plants, no matter how fancy, even the wind farms out there, they're just turning a generator. So since they're moving like this, the current that's generated actually alternates back and forth, and it comes directly because every time we generate electricity, the only way we really know how, except for solar panels, we're doing it by rotating a wire inside of a magnetic field, which is what's inside of a generator. Because of that motion of rotation is a direct result of how we get alternating current, and that's really the reason why the power plants do that. When we build a battery, it's a chemical reaction. It's either on or it's off. There's no motion inside of a battery, right? So it's just going to give you that constant deal, the constant current, the constant voltage. So that's the difference between DC and AC. In this class, we're going to focus on DC first. We're going to learn all the techniques of analyzing DC circuits, because really when you get to AC, once I show you the method, it's really not that different. So we're going to do DC first, get really good at it, and then we're going to introduce the alternating current mechanism. Just a couple of other definitions I want to get to real quick before we call it a day. Everybody's heard of this. What is an open circuit? What do you think an open circuit is? Well, if you have a circuit, right? If you have a circuit, it's supposed to come all the way back to where it started. If you have an open circuit, it means somewhere along that path it's broken, basically. So an open circuit would be if I had some kind of source here, like here, and then I had a break in it, make this break a little bigger, then there's no more current flow. You cannot have current flow in an open circuit by definition. So this open here, this is what your wall switch does. When you flip the wall switch, it just breaks open the circuit so no electricity can flow anymore. That's what we call an open circuit. Now let's also take a moment to talk about a short circuit. Short. Lots of people have heard of short circuit. Most people know that short circuit is not really a good thing, but a lot of people don't know what a short circuit really means. When you think about it, if you have a circuit, you've got a source and you're supplying energy or electricity to some load over here, we call it. Could be a light bulb, could be a fan, could be anything, right? So in general, for every circuit that's operating, we're going to have something over here that we're supplying power to, right? This could be anything at all. I'm going to put a giant box here. This could be, a fan, for instance, right? And this electricity is coming out, this current is coming out into the fan, causing the fan to turn, and I'm leaving a lot of details out, but that's basically it. Now, inside of your circuit, let's say somehow a piece of wire kind of accidentally connects from here to here. Maybe You're working in a building, let's say, you're building the building, you're pulling the wire through the building, and somehow a stray piece of wire gets connected to two terminals like this. Or maybe inside of your lamp, you develop a short circuit because the two wires that are supposed to go to the light bulb, maybe they start to touch on accident. Well, what happens is the electricity is coming out here, and when it gets to this junction right here, it has a choice to go this way through the fan or this way. Now let me ask you a question. What do you think is going to be the lower resistance? Do you think it's going to be lower resistance for the electricity to go through this giant fan and spin something around? Or do you think it's going to be a lower resistance for this electricity to try to go through this little piece of wire that you put there? It's going to be much, much easier for the electricity to go through the wire. And so electricity is always going to do that. It always tries to go through the path of least resistance, just like you do when you're in traffic, right? You try to go to the path of least resistance. So because of that, the electricity never even gets to the fan. So that's called a short circuit. It's called short because it kind of truncates the circuit, or it shortens off the circuit. And it's very bad for lots of reasons, but because whenever you start to get current going through a wire like this with no resistance or very low resistance, you can actually generate a lot of heat, and you can actually cause a fire, actually. And that's why you have those circuit breakers outside of your home. Those are there to detect if any short circuits happen, to detect the extra current, the increased current that comes from it, and to shut them off. If you get any kind of a short circuit in your washer or your dryer, maybe some wires start to touch, the current is going to start to go up really, really fast through this tiny little leg, and your circuit breaker is in the circuit with that. It detects that, and then it shuts the circuit down. So that's basically how that works. That is about all I want to talk about in this lesson. We've covered a lot of things. We haven't done any math. That's okay, because sometimes in the beginning you really need to take some time to understand the fundamentals. So we learned about the circuit. You always have to have a complete circuit to have any electricity flowing. We learned about current. It's the flow of electrons in real life, but in a circuit analysis we don't talk about that. We talk about the positive current going in the other direction. Has a symbol of I. All right? In terms of our equations, right? The unit is amperes, or A. Of course, we can talk about milliamps, microamps, kiloamps, things like that as well. And then we talked about the voltage, which is related. The voltage is the push that pushes the electric current around in the circuit. The higher the voltage, then the more push you have, the more current you're going to end up getting because you're pushing through with more force, for lack of a better word, right? The units is a voltage that we talk about, or of course you have millivolts, microvolts, etc. And then we talked about resistance, which is integral to all that. That is sort of a property of the circuit, or the property of the wire, the property of the components. And it literally tries to oppose the electric current. The unit is the ohm, which is the capital omega here. Of course, you could have milliohms, microohms, kiloohms with that guy, just like you have for the others. And then we talked about some other random definitions that people have heard over the years of growing up. Direct current DC, alternating current AC. This guy is usually coming from a battery, some constant current source, usually a chemical reaction is giving you a constant voltage, constant current coming out all the time. Alternating current comes out of your wall. The reason it's alternating is because it's easier to generate, because you have rotating generators and you have easier transmission to the homes. There's a lot of theory in that, but that's basically the deal. And both are electricity. The fact that it alternates doesn't really mean much. I mean, your light bulb, you don't see it flickering, but the electricity is actually going through your light bulb back and forth 60 times every second. You don't see it because it's so fast. So don't get too wrapped up or hung up on the difference here. They're both electricity. They both deliver energy. And then we talked about open circuit. You have a circuit where you literally take a piece of scissors and cut it open. No electricity can flow anymore. And a short circuit is when you have an operating circuit that you accidentally bridge or connect two pieces across together, and it basically causes the electricity to not even go into the load at all. So the load stops working, you get tons of current built up here, and it can actually lead to smoke and fire if you let it go, and that's why we have those circuit breakers in our homes. So that's what we want to cover in this section. The title was Voltage, Current, and Resistance. It's so important to understand, so make sure and watch this until you feel pretty comfortable with it. The next few sections, I want to do some more background stuff. We'll talk about taking an overview of the circuit components out there, and then we'll do another lesson on what we call Ohm's law, which in mathematical terms relates resistance, current, and voltage together. And I promise you, Ohm's law is so simple that it'll just boggle your mind. It's very, very simple to understand. And then once we get those foundation things going on, then we can really start diving into some real circuits and looking at how the current's going to move through the branches, how they're going to sum together, what's going to be the value of the voltage here, the voltage there, and then we can get into some more complicated circuit components like capacitors and inductors, and much later even what we call transistors and diodes and things like that, and you'll be introduced slowly but surely over time to this beautiful thing, I think, that we have in the 21st century called, electric circuits. So the nice thing about it is you can learn this stuff, you can, academically understand it, it's good for your career and things if that's what you plan to go into, but also you can take a trip to the store, buy a few components once you know what you're doing, and you can build a radio if you want to. You can build a blinking light if you want to. You can build an alphanumeric display if you want to. So it's one of the few things that you can really learn that once you understand it, you can really go out there and build it. If you learn about nuclear power plants, they're amazing, but you're not going to be able to go build a nuclear power plant. If you learn about Einstein's theory of relativity, it's amazing. I love that stuff, but I'm not going to be able to really test it myself. But with circuits, once you understand it and learn it, you can actually play around with it, and that's what I find so fascinating about it. So I hope I've kindled your interest a little bit. Stay with me. We're going to go through the sections and dive into all of these circuit analysis techniques. I'll try to make them as simple as possible, but you do need to practice your problems. Practice problems that we present here and also the extra problems that are in your textbook.